Good evening to those in India. We have Dr. Begovic from TAMU and his student Jorge Cisneros, who are presenting today, novel relaying techniques for distributions and microgrids.
Good morning, everybody. Thank you for introduction. My name is Miroslav Begovic. I'm a professor and department head of electrical engineering at Texas A&M. And Mr. Jorge Cisneros Aldana is a PhD student working with me on this project. The topic that we will discuss today is somewhat misleading: novel relaying techniques for distribution and microgrids. We will actually be discussing developing a test bed for those testing and discussing some of the techniques. So we know that over the past couple of decades, distribution systems have changed a lot, partly because of introduction of so many power electronics interfaces of the loads, but also because of the presence of new types of loads, such as plug-in hybrid cars, electric vehicles, new types of HVAC and other devices that have power electronics interfaces. All of that is making interfacing distribution with the rest of the grid and with customers more complex. Microgrids have evolved as an option to run autonomously or semi-autonomously such systems under circumstances that require it. And they are bound by their own rules. Much of what traditional power systems are doing can be scaled down, but is different from what is implemented in microgrids. And this is really the topic of our conversation today. Much of the new generation, however, exists or will be existing in distribution, on distribution side. To give you an example, 10 years ago, I was still professor at Georgia Tech in Georgia, and there was 0% of solar and wind renewables in Georgia power grid. Today, there is 3%, which is huge, considering that we went through one major recession and one pandemic and all of that in that time frame. So inverter modeling that is presenting an interface as a generator instead of traditional rotating machines is also part of what modern microgrids entail. And then we need to investigate operating conditions, usual and unusual, as well as fault conditions in order to be able to detect and simulate the circumstances under which the relaying should be effective. And the purpose of this presentation will be for me to give you a short introduction and let Jorge present some of the tests and model development effects that he has worked on in order to be able to play with the protection ideas for autonomous AC microgrids without going into hardware and burning the actual equipment. Once we are sure that what we are doing is right, that stage may come. So microgrid is a localized group, formally speaking, of electricity sources and sinks that can be either connected to the main grid or operating independently from the main grid. And as we see here, it has renewable resources such as wind turbines and solar that can be scaled from a few kilowatt to a few gigawatt. And then it may contain other traditional generator sources like rotating machines driven by gas turbines or diesel generators. It can contain energy storage, but it may still be connected to utility and have load. So all of those things could, but not necessarily have to, be part of a microgrid. When we look at, from the generation side, inverters, which are part of PV interconnection with microgrid, have several layers of control, nested layers of control, which contain primary control, most important for us, which is regulation of current and voltage and preliminary power sharing to balance out the system. And then secondary control deals with issues in the seconds time frame as opposed to milliseconds, where primary is acting on voltage restoration, power quality enhancements, and so. And tertiary, which is not at all topic of our interest at the moment, deals with issues like power management, energy management systems, and dispatch, which is fulfilling all of the roles of traditional power systems, but in a small scale. Let me just introduce through a couple of slides solar, just to give a little bit of a perspective. Technology of solar is very similar in certain ways to development of organic life, and that's what the right-hand side slide shows. On the upper side, we see a cross-section of a typical solar cell, which can be made of multiple materials, but by and large, most dominant technology is crystalline and polycrystalline silicon. Those are very thin, 180 micron wafers that are doped with materials that are providing an excess of ions in the grid that is serving the purpose of enabling photons from the sunshine coming through the upper surface to be used as a source of energy to create free roaming electrons in the wafer. Those roaming electrons either recombine back into the crystalline structure or get attracted to electrodes. You may see at the top of this slide the kind of a fork-like electrodes on the top end, and it's a solid on the bottom. That creates a continuous flow of electrons as long as the solar flux and photons are hitting that surface. The efficiency, because of the process being related to quantum mechanics, doesn't allow more than about 35% ideal efficiency, but practical efficiencies are now hovering between 17 and 22% for commercial grade models. When we look at organic matter, it does a similar thing, but through chemical reactions using carbon dioxide and water to create carbohydrates, effectively storing energy in them. And all living beings on our planet are using the results of that process called photosynthesis to run the energy systems through our own metabolism. So there is more than symbolism in the presence on the left-hand side in this photograph, the tree and the solar photovoltaic system modeled, designed to look like a tree because they're both using energy from solar. Here is what a real small solar network might be. This one is not the greatest accomplishment in design given by the number of tiles that are standing around it. But typical solar photovoltaic roof mounted systems are a couple of kilowatts, no more than 4 kilowatt, and they are linked to small inverters like the one shown on the right. You see that inverter has a lot of capacitors, and those are the critical elements of what drives the lifetime of the system. So whereas solar panels can last easily 30 plus years, inverters rarely last more than half of that time, and they have to be replaced or substantially refurbished to continue their lifetime beyond that level. Here is one system that I can claim a little bit of ownership of. That's the Georgia Tech Aquatic Center photovoltaic system, designed and executed at the time of the Centennial Olympic Games in Atlanta. Several of us at Georgia Tech have developed and designed this system. It has about 2,800 solar panels in polycrystalline silicon technique. They are about 11 to 12% efficient for the overall system efficiency of about 7%. On the inset on the lower left, you can see what it looks like from the walkway in the middle of the barrel vaulted roof. And at the far end, you can see the solar thermal system that was built at the same time for the purpose of using solar energy to heating the water in the pools. This system has been in continuous operation for some 26 years, and it's been operating marvelously well. It's rated to about 340 kilowatt. It's producing about 400 megawatt hours per year. And for a while, about 3 months upon its construction, it was the largest roof-mounted system in the world, but it was soon replaced by others, slightly bigger and slightly more efficient. However, it served as a great test bed to faculty at Georgia Tech. Someone is keeping their sound, so I'm hearing the echo. Thank you for toning it down. This is how the solar PV systems can grow large. The picture on the right is one of the largest known systems in China, built in Huanghe Hydropower Development Corporation. It's 2.2 gigawatt. That is reaching the size of large nuclear power plants. And you see that it covers a huge surface area, but it is a source of solar power. Another one on the inset on the left is the 13.7 megawatt system that's been built on the surface of a lake. Another unusual place, but important when the real estate prices are high and the land is needed for either agriculture or for construction. So all of those things are fulfilled. Inverter application, inverters who are driving these solar photovoltaic systems can be single phase, three phase, can be on the roofs of the houses, or utility scale PV, which is now beginning to proliferate to a bigger extent. And all of those things could be part of the new distribution, even more medium voltage level for interconnection or utility scale systems. But generally, distribution is what we are talking about and what will be the subject of our talk. So what happens with protection when we are talking about it? If we have a distribution feeder similar to the one represented here, which I borrowed from a presentation from colleagues in GE Energy, this distribution feeder has distributed generators in the form of power plants, PV plants 1, 2, and 3, labeled and presented here, and they can start contributing to the loads, which are shown as arrows. Feeder 2 and feeder 3 can be viewed as loads from the 13.8 kilovolt bus bar, but they can be scattered across these lines. And instead of unidirectional fault current coming from the substation, where the generator representing the rest of the transmission network, an LTC load tap changing transformer representing the substation are situated on. So current is coming from the substation, but it could be coming from PV. Load is changing all the time, and so does the PV production. So the levels of the fault currents and directions that the fault location represented in the middle of that picture is attracting current into itself can be multiple. Those conditions change, and traditional overcurrent delayed, time delayed protection may be inadequate to capture all of those situations. So those circumstances have driven us to consider alternative solutions. Adaptive overcurrent protection is still doable, but it could be and should be coupled for mostly radial networks, so to say, with directional overcurrent protection having dynamic settings for the reasons we mentioned. Settings can no longer remain the same when you have multiple generators and the rapidly changing load levels in the system that did not exist before when traditional overcurrent protection relays were designed. It could also be done using more advanced approaches like reinforcement learning or any types of machine learning. And those approaches, I would say, in all fairness, are a matter of speculative and motivational studies at the moment rather than being emerging technologies. However, distance protection, which is taking into account both current and voltage measurements like it does in transmission systems, could be a candidate, but the problem with the feeders and with the microgrids is that the lines are rather small. They could be a couple of 100 yards or maybe a mile long. Distance protection requires a better resolution in finding that, so the resolution and accuracy of distance protection pose bigger challenge to the relays that would be based on such use. Then differential protection, of course, would be great, but physical distance between the ends of the zone that differential protection would be covering are really limited. So it is something that we shouldn't really consider as feasible unless the microgrid is on a rather small area. And then directional comparison protection, which is based on phasor measurements, that Jorge will say a few words about towards the end of his presentation. We have reached that point, and I would like to transfer the presentation to Jorge to continue telling us how he has developed this this test bed and some of the ways in which he has tested them. Jorge?
Sorry, Professor, I was muted by default. Good morning, everyone. Can everyone see my screen? I'm trying to...
Yes, we can see it. We can see it. Inverter model. Okay, correct.
So basically, following up Professor Miroslav Begovic in presentation, I will talk about this example about how a microgrid is connected. So the content I will cover today will cover a portion of inverter model verification, microgrid model, asymmetrical faults, PMU verification, some related principles and applications that we will address specifically for our case studies, and distinction about kind of faults and that kind of loads that can create confusion between the grid and whether decide as a fault or not. So here the figure can see the critical part of the model. So this is a microgrid that is connected to a traditional transmission line through the point of common coupling. So our focus now is in an autonomous mode type of grid, which basically consists of PV solar panels. They can be rooftop or also in a not rooftop, like on the floor. And the portion here I want to address is we will cover the building state, how we reach a very realistic type of a scenario for building the inverters, the model itself, the microgrid model, so we can basically test with higher accuracy the protections and the development of the relays. So regarding the inverter model, I will talk about a little bit about the control, some validation we did, the validation of the Drup method that is implemented in this one. So as Professor Begovic mentioned it before, we have two types of levels. Level 1, which is the control loop, the local, and the level 2, which is the inner control loop. The most important part of these two is to know that the level 0 requires a faster control level, which should be in the range of milliseconds. And the level 1 is a slower type of control, which should be in a range of a few seconds. Here are all the blocks, the control levels that the equipment has. I will show in the next slide a little bit of more detail about this. So basically, this is our inverter, how it was modeled in the Simulink, which is the software we are utilizing for validation and testing our experiments. In this portion, we can see the control block, which is basically the level 0, level 1 that I presented before. And as input of the grid, we have a solar PV system. This usually is, we are considering here a DC link, and this DC link usually is in voltage, direct current type of voltage. So as we can see, in order to connect to a traditional grid, we need to have an AC three-phase grid, which is the one we are utilizing basically mostly everywhere by traditional means in distribution level. So our inverter is doing the interface of connecting our solar panel in DC mode into our AC. This is the filtering stage required. Here I'm showing the control block of our inverter. Basically, we take the measurements of the voltage and current after the filtering. We calculate the different power, active and reactive power. We apply the Drup control for the frequency from the voltage reference in order to create a reference of voltage. After this, we cross to a transformation from ABC to DQ0 reference frame, which is the common reference utilized for controlling microgrids due to its simplicity of converting a three-phase signal into a more simple TQ coordinate. So from here, we create the reference voltage. This reference voltage is fed into a voltage control loop, which includes a PI controller, basically a PID, but we are utilizing only a PI in order to set the reference current. This reference current is passed to a current limiter. We are applying the instantaneous saturation limit, and in order to prevent the inverter from burning, damaging, or having thermal damage from the internal components that it has, the semiconductors and everything basically. And from here, we utilize the current control loop, which basically has the PI controller as well, to generate the voltage reference. This voltage reference we also pass to a voltage limiter for fault condition in order to prevent over voltage or under voltage to not further damage the inverter, and additionally, if we keep in this operation the equipment that is connected to it. From here, we connect into the pulse width modulation. Here, we know there are three types of mainly inverters, which is the grid forming, grid following, and grid supporting. The one we utilize is basically built as a grid forming type of inverter, because we need to control it as an autonomous grid, be able to control the voltage and the frequency by itself when it's not connected to the microgrid. So here I'm showing a quick example of what I presented before. So where are our blocks connected? So this is our control block model in Simulink. So here I have the droop control, which creates the voltage reference based thanks to the virtual impedance. And from here we can pass to the voltage regulation. And here I'm marking the current limiter, which sets up the current reference in order to not burn the inverter, as I mentioned before. And after passing to the current regulation, we have a voltage limiter. So this also prevents, as I said, the over voltage and under voltage. So during faulty conditions, in normal operation, these limiters don't interact each other. So for our test and validation system, we built an inverter that has a 30 kilovolt ampere capacity. Our DC link is 750 volts. Our grid level is 240, and our frequency is 50 hertz. I think these are the most important portions. Here we'll be testing step load, we will be testing ramp load, and we will be testing during a simulation in different time steps in order to see the event and the response, in order to validate the model. Here we can see the different powers utilized. So we have reactive and active and reactive power, both together. So the first test includes a step type of load introduced into an already functioning grid. So basically, at the 0.2 seconds of simulation, we introduce a power, which is step type in active and reactive mode. So as you can see here on the right-hand side figure, how happens the jump when the load kicks into the grid, and it settles down in less than a cycle, which shows how the control system is working. In this following figure, I'm showing the same case study, but here we have voltage current, voltage RMS, and our frequency. But the most important figures to notice are the voltage and the current here. And as we can see, we have some small transient when the load kicks in. And thanks to our controller, we were able to, in less than a cycle, being able to continue operation of the inverter. Here I'm testing a ramp type of load. So we know that in houses, we not always have step type of loads. We might have an AC, or we might have a shower that is electrical. So some of them, they do have this type of behavior. So it's critical to test this type of response in an inverter modeling. So as we can see, this is entirely resistive load, which is adding just active power. And we can see how so a critical point here is to notice that the grid already has loaded introduced to it. That's the reason why it's not here in 0 from the previous slide that I showed. So here we are basically adding a new type of load, which is kind of traditional type of operation. And so as we know, we keep adding and removing loads basically all the time. So we can see that how the inverter responds to this type of load and how it settles down until it reaches the maximum point. So again, here I'm showing the event. We can see that the ramp load basically starts between 0.25, 0.27 seconds here of simulation, and how the current, it keeps going up until it settles down in steady state. The Drup control algorithm implemented. So the Drup control basically helps us working in an autonomous type of grid and also in a multi-inverter grid connected that it is not connected to the main grid. So our Drup control will help us share the load between different inverters connected and to do it without having communication to every single of the inverters. But by this case, so we can prove that when we introduce a new power, we have a drop in the omega, and when we introduce a new reactive, we can have a drop in the voltage reference. So here I mentioned what are the portions of the Drup control that we are utilizing, like the frequency, the reference voltage, the active and reactive power, how it relates active with the frequency and the reactive with the voltage, how the frequency can step down. So here I'm proving how the Drup control is reacting to a step type of load. And as we can see, the load happens here on the right-hand side figure. I will just show the frequency and the voltage in RMS to better understanding. So when the load kicks in and it's a active and reactive load, we will be having a small drop in the frequency, so does a small drop in the voltage, and then we continue to steady states. In the following figure, I'm showing same case study, but in this case, we are introducing a step type of load, which is entirely resistive. As we can see, as the Drup control literature mentioning, we have a drop in the frequency, correct? But since our load is entirely resistive, we have a transient when the load kicks in and it settles down in basically the same previous that we have. So our voltage is not reducing as we expect. And this event happens in a cycle. So the microgrid model we implemented, we will be introducing the same inverter we utilize that I presented before, but now since we validated the test on how the internal control system is working, now we will work in a bigger scale. So with connecting more loads low with medium voltage levels and parts from the study. So our grid voltage is 240 volts, our frequency again 50 hertz. Here we will be testing two types of generators, the inverter and a synchronous generator, in order to contrast the response to each other. We have here the parameters of the LC filtering that we calculated for our rated power. We have a transformer that is stepping down from low voltage into medium voltage to replicate a distribution line, which is 4.1 volts, kilovolts. Our distribution line is averagely a 1 kilometer, the one we study. We did other representations, but we're trying to be so close to a real case scenario that we can be in a small village or where we have this type of condition interacting with the grid. So we test tap load. We will test also the low voltage load power. We will test different fault impedances. So in our case, I will just show the 0 ohm impedance, which is when we have an event that happens in between the grid, and we will contrast this with the different type of powers that are called introduced to the grid. And the limiters that we defined previously, we are utilizing 1.2 based on the literature. That is a nominal point to prevent the inverter into have thermal damage. So here we have the two test studies we validated back to back. So on the upper figure, you can see we have a generator, a synchronous generator, a traditional synchronous generator, which is a rotating machinery that is connected into low voltage. And we up this into a medium voltage where we have a short type of distribution line. And then we step down and we have the consumer level here. So we are contrasting this case versus the same case, but instead of having a traditional generator, we will be having here an inverter. The inverter we developed, and I explained in the previous slide, to see the response during all these different scenarios and conditions. So regarding the short distribution line, we are utilizing a line which is 1 kilometer. Our voltage is 4.1. This is how the line was modeled. So we are utilizing, this is the Simulink model, but this is the literature example, as we can see. And the shunt capacitance here is neglected due to the length of the line, because we are working in short type line mode. For our transformer connection, we know there are different types of connection between YY, Y delta, delta delta, Y delta, and also Y grounded modes. So we are trying to utilize the most common ones seen in distribution levels, which is basically delta Y and Y to Y. Delta Y is far better because it traps the third harmonic in case we have some faults. So we tested these both critical for our case study. So these are the two type of connections that we can see in the higher end and in the lower end, which we are going from 4.1 kilovolts up in medium voltage and reducing it to 450 volts in low voltage. This is the transformer utilized in Simulink that has the parameters inside. So here I'm showing the microgrid model that I showed before. Since I already explained, I can just go quick about this. So we have here the inverter connected in the left-hand side with our synchronous generator, and also we have an ideal voltage source to see the response with each one of these kind of generators. On the left-hand side, we have different type of loads. We have a step load, we have ramp load, we have constant power, we have like all the ones we can see in a house. So here we can see the different transformers utilized for the model. Here we can see the distribution line that I mentioned it before. And here we can see the blocks where we are testing the different type of faults and the tap load. So we are showing the short faults, which is the most critical. And then, so this is the inverted model that has a 2-bus model. So here we have, compared to the previous one, which is the testing mode, we need to also study the inverter, how it reflects into a microgrid that has more connected systems to each other. So we have in 2 different buses, 2 different inverters generating power in low voltage. This goes up to distribution line, and they connect to a 3rd bus, which is basically having all the loads. So here we are validating the droop control, the load share, the different limiters, and also the different events that might happen. So we might be testing a fault in the line here, or it can be in this other line. The reason why this is split in 2 is because we want to test in different locations of the line. We know always doesn't happen. I mean, it can happen closer to this line. So with this, we set up the different ends of the line. And here I'm showing this previous slide in a bigger system. So we can see we have here the 2 different inverters in bus 1 and bus 2. We have here the loads in the bus 3. We have here the fault blocks and the tap load. We have here the different transformers utilized from going from medium voltage to low voltage. We have here the distribution line. So now I will show a little bit of the fault verification and to see the response of the inverter. We are comparing with a synchronous generator, as I said. We are testing the most common type of faults, and we will be seeing the response of the limiter. So in this following figure, as before, in our study case, in our experiment, we will be testing a fault during 0.5 seconds of simulation. We are not triggering any relay because, as you can see here, they are not implemented yet. And the reason is why, because we want to understand the response of this generator under a faulty condition. We tested, as I mentioned, the YY and delta Y types of transformer. So here is the same grid with the only synchronous generator, and here instead of the synchronous generator we have the inverter installed. We are taking all the measurements in the lower voltage at the lower end of the transformer connection. So these are the most common short type of faults that exist: the single line to ground fault, the double line to ground, and the triple line. So we know that the incidence of this fault is like 70% the single line to ground fault, which is the most common one, then followed by the double line to ground fault, which is 20%. We have a line-to-line fault, which is 10%, and we have a line-to-line and line-to-line ground fault, which is 5%, which is the less common, but is the most critical. But all of them are critical in our study, to be clear. We utilize an asynchronous generator for comparison, and we use the inverter to validate the response of them and current research and experimentation. So here I'm showing the inverter validation model under different faults. On the both figures that I'm taking from the previous figure where I'm taking the measurements, we know that we are contrasting how a synchronous generator behaves on the left-hand side, the voltage and the current at the moment of a fault, which in our study case, as I mentioned, is a period of 5 seconds, which is here. And on the right-hand side, I'm contrasting this one to our inverter model including the voltage and current limiters that we implemented into this one. And it happens at the same time. So the figures might look the same now, but if you pay a little bit of attention, we have the peak current, which is very high in the synchronous generator as expected, and any fault, as we know, this happens always. And we do have on the left-hand side the inverter peak current, and we can see that in a less than a cycle, we can able to trim it and limit the current in order to prevent the inverter from damage. So the magnitude is totally different between this one. So this is a good point to address. So here I'm testing the same case of study, but for a line-to-line ground fault. And again, the fault happens in 0.5 seconds. We have on the left-hand side the test system from the synchronous generator. On the right-hand side, we have our inverter model with limiters implemented. And again, we have some small jittering, correct? But after the less than a cycle, we can have the trim version that is what we are expecting for, based on the parameters we define to prevent, again, as I said, inverter for further damage. And also it's good to mention that our figures might look alike a little bit. We can see that the magnitudes are totally different. That's the reason why we need to do a different type of detection when we have faults in inverter connector. Here I'm testing a line-to-line to ground fault, and again at 0.5 seconds, and again at 0.5 seconds. And we have the peak current at the magnitude, as you can pay attention, is way smaller comparing the inverter versus synchronous generator. Now here I'm testing the line-to-line ground fault, the triple phase fault, again at the 0.5 seconds. And as you can see, the peak current is the critical factor here. So we are able, thanks to the limiters, we were able to reduce this current into what we defined, which was 1.2, in less than a cycle. This prevents the inverter for further damage, as I mentioned before, and all the thermal damage and all the semiconductors and all, basically for stop functioning. So how we model the PMU model in order to detect this type of faults. Here I'm showing a back-to-back our model in Simulink and our online diagram in order to better understanding what we model. So basically on the left-hand side, we have a transformer in low voltage to medium voltage. Here we deploy a relay. We have our short distribution line, and on the other end, we were having another circuit breaker and relays, and our transformer to go from medium voltage to low voltage. And we need to have a communication between these two ends in order to be able to share what we are seeing in each other end, which is one critical part for the relays must talk each other. So our characteristics of the system, our phasor were calculated by a recursive DFT over a full cycle. Our sample frequency is 400 Hertz. Our nominal frequency is 50 Hertz. And we are testing at both ends of the line. So we will call it, for this example, bus 1 and bus 2. In the medium voltage side of the line, we are testing a fault. We will test all the common faults I presented earlier. Also, we will test a tap load, which means instead of a fault, we have a tap load connected between this line, and to see its response, to contrast it, how this doesn't affect the detection method it was proposed. So Yeah, I know this figure is a bit heavy, so I want to be clear. I will explain this in fewer slides. So basically, we have a two-end event comparison. We take the measurements of both ends. We check the current flow direction, and we set up the different relays pair to register whether exists a transition or no in your cosine signs. Well, I'm testing the cosine signs. So basically, our model proposes measurement the current in the three-phase measurement, doing a positive sequence calculation, passing to a discrete Fourier transform. We use in a phase angle calculation. Thanks on this, we obtain the cosine value for monitoring the sign, which means the direction of the current. And we have on the other end checking whether it changed or not in order to trigger some relays. Here I'm showing the mathematical model of the same here, so I will skip that one. So the cosine values basically are computed in each relay independently, and they are shared to them. So we register a small change in the cosine of sine after the fault inception happens in order whether to detect we have a fault or not. So here I'm having a clear figure of what I said before. So basically, we have in one end of the line measuring our three-phase current. This is the model implemented in Simulink, the bottom one. Here I'm showing the block diagram of the same model. This only shows one end, it's not showing both. So we do have we use the recursive DFT transformation over a full cycle in order to obtain our steady state of the phasors. We pass this to a positive sequence transformation in order to be able to calculate the cosine and the phase angle in a more consistent way. So we are utilizing the nominal frequency for the recursive DFT algorithm. And from here, from the distance, we can obtain whether it's positive or whether it's negative, the cosine of the angle function. I will talk about this to validating our recursive DFT model develop. So when we have a step load, I'm showing in the blue line the magnitude and the red in the orange one the angle. When we have a step load that happens in 0 to 2 seconds, we can see how the response settles down in a cycle, in a matter of a cycle, thanks to our recursive DFT full mode in order to reach full state. But we can detect in the earliest state that we are having some eventuality just thanks to our frequency rating in the early time. So here I'm showing the recursive DFT response at the end of the phase A. We know we have three different phases, so we're testing here to show the different phase A. And on the bottom one, I'm testing the same scenario in a positive sequence calculation of the current. We can see the responses as expected. This signal is better to detect because we are converting the three phase signals into a one positive one. And we can detect that in a matter of a cycle, we were able to reach to a steady state in operation, which is the common post-disturbance in all DFT models. Here I'm testing the same case scenario, but with a ramp load. Again, I'm testing the recursive DFT in phase A and the positive sequence. As we can see, our ramp happens between 0.25 and 0.27 seconds. After this, we need a cycle in order to be able to reach to a steady state. And in the positive sequence figure in the bottom, we can see how our signals look better, and also we can have this earlier detection. So I'm passing to the here. I want to show how this model works. So how we discriminate faults versus a tableau. So basically, we have in our case two bus systems with two inverters. We have an inverter and its load, and on the other end of the line, we have another inverter and two different loads. And we know that thanks to our loop control, we will be able to share the load between them, how much they need to give to the grid. And in the middle of the line, we will be testing a tap load and a fault. We know that any event can happen here, and not just in the middle. It can be here on this end, on this other end. And that's why the reason we want to show how the relays communicate each other in order to detect this type of fault or eventuality. So now I will talk about the cosine function of the angle and the sine, why we do this and why it's important in our method develop after we verify our recursive DFT block diagram develop. So here I'm showing an illustrative example of the previous model that I presented before. So we have an inverter that is injecting current to the to the load in the bus 1, and on the bus 2 we have another inverter injecting load to this step and this ramp load. And here we have a share load current, and these our relays should be able to talk each other in order to detect a fault. So our method developed before based on the cosine sine of the angle, which is basically the rate of change in a fault or in any other event. The blue lines present a pre-state of any event and how the current is flowing. So we know that this inverter is feeding this load, is feeding the distribution line, and is also feeding this load, and the other inverter is feeding this load and feeding this load. So this is how we are sharing the load here. But now we will test how it happens that when a fault happens. So here I'm showing that it happened a fault in this portion of the line. So how our relays will be able to detect this based on the cosine, the rate of change, cosine, and the sine. So basically, these are the post-event state current flows that we have. And as we can see here, we register a change of direction, which the relay of the second end is seen, but the relay of the first end is not seen. So we need to be able to talk each other in order to say, okay, yeah, there is a fault here, or there is a tableau, or what event is happening. So here I'm showing the study model we did. So we have two inverters here. We have a load here. We have the transformer installed. So we have two bus inverter. It's the same model I presented slides before. We have the distribution line. We have the fault, the tableau will be tested, and we have the different circuit bus deployed. I know the figure is heavy. That's the reason why I'm showing with the arrows and to explain which this figure represents for. So here we tested the line to ground fault. And as we can see, when the line to ground fault, the double line to ground fault happens, I'm showing the rate of change in cosine function on the upper figure, and on the bottom I'm showing the sine comparison, which is the sine of the cosine of the angle that we were measuring in the upper figure. Our frequency of the grid is 50 Hertz, and these are measuring just in the line that is talking with each other with both ends, the one I presented a few slides before. So the blue line represents the bus 1 end, and the orange one represents the bus 2 end. And we can see that when the fault happens, we do have some small variation in our cosine of the function. And if we take the sine of this, we were able to detect that the load is flowing to the other way, as presented in the previous example. So whether the previous state was everyone to the feeding from 1 to 2, in the second state we have one feeding to 2, as we said here, but the other one we can see that the current flipped the other way because both are feeding the fault, and this changes into negative. Here I'm testing the same case study for a line to ground fault, and again we have the fault, and our cosine rate of change, cosine phase angle, and the sine comparison helps detecting the fault in an early state in less than a cycle. So as we can see in these discrete figures, we have the inception of the fault and how we are able to detect it due to the change of signal, because as I said, the current is feeding the other way. Here I'm testing, in contrast to that one, a tap load, which basically our tap load here happens again at the same time, 0.5 seconds. So I'm trying to see how the relays detect this tap load, which is different than the fault. And we can see on the bus in the blue line how it's detecting from end number 1, and in the orange one we have the end number 2. And we can see that when the tap load enters, since both signals don't detect a change in current flow, we were able to detect that the cosine of the angle is still positive. So our relays won't trigger in this case scenario. So here I'm doing just a comparison over a 3-phase fault to compare how a fault will behave contrasting to discriminate a tap load. So the rate of change of the cosine in the three-phase fault, we have the event happens, and as we can see, these are the cosine response of the both ends of the line of the currents. And in the bottom, we also have the cosine response of both ends of the line currents, and we can see that it's the figures might look like, yes, it happened a change, but if we pay close detail, we can see that the change in the second figure is still in the 90 range, which is basically, this is the power factor of decline, and how the first one, it changes. So the same figure, checking from the node cosine comparison, the sign comparison, this is how the relays is going to check and to decide whether exists a fault or not. So in the first case, we have the positive, which is represented by -1. So we have a fault happening, and we have to be able to detect event in an early stage. On contradiction, when we have the tap load, we don't have a detection in the rate of change. So we can say there is no fault here. And here I have the conclusions. I would like Professor Begovic to speak.
Yes, I will just join in because we are running to the top of the hour. Conclusions are to be expected, but the focus of our work is on AC microgrids alone. But given the number of different types of inverters and situations where both inverters and small rotating machines may be in the network, the level playing field of test beds to be discussed is almost infinite. And we are focusing here on certain types of inverters, certainly grid forming and grid feeding and supporting inverters of the rather conventional kind, but there are many flavors in which this discussion can go in. PMU technology that we are using for testing the concepts of these protection types are saving grace compared to, for example, differential protection to be used in the same for the same purpose. But the versatility in the model is the simplicity of circumstance that is being detected, and therein lies the potential danger of overlooking something or not seeing the models of the kind that could be used in the real world. So we are going to provide as exhaustive testing as we can. Very small information content is needed for communication. It could be done in conventional ways or using more modern communication. Effectiveness is that it could isolate only the faulted line, which is a European practice, as opposed to US, where usually all three phases are cut at once, stripped at once. And we keep on developing these things and marching towards creating an encompassing study that will include both traditional active distribution feeders enhanced with renewables, as well as these microgrids. So we'll stop here. We may still have time for one or two questions.
There was one question in the chat earlier.
Okay, how do I get there? I'm trying to see.
Here, I can read it. It says, whether the peak current and the transient response depends on limiter or current strategy used for the inverter. Is it possible to change shape this response by a different control scheme?
It is entirely within the realm of possibilities that tuning the control of the voltage and current and the control algorithms of the limiter may affect that. That has, I should say, not been the topic of our study because the protective algorithms that we are testing are relatively new. And we would first like to ascertain their robustness and reasonableness of use. And there has been couple of papers published from earlier work of our collaborators before this project began that validated that concept, but in practice it has not yet been validated. And having seen a lot of simulations with different types of controls in inverters, I couldn't say no, but I would be speculating the same way that people who are trying to judge the source of the COVID-19 virus are trying to see where is it originating from. My answer is yes, probably yes, but it's not within the framework of what we are doing right now. Any other questions? Okay, if there are none, I will turn it over to Noel and Anurag.
All right. Well, thank you very much for your presentation and for helping us. We got the technology working at the beginning. We appreciate that. And if there are no other questions, we will remind everybody that we will have at the end of June, we won't have any webinars the next 2 months. In June, the week of the 21st, we'll have our UI Assist US theme meetings. We got an email last week about that. And then the first week of August, we will have our workshop with India, and then some theme meetings in July. So more information will be coming out in the near future. So thanks to our colleagues at Texas A&M for jumping on after we moved some meetings around so that we could have this webinar, and for their interesting talk on these different perspectives. So thanks everybody for being here. Have a great day.